So hello and welcome to my YouTube channel. So we have already seen the first part of the Kirchhoff's law. There were two laws I already discussed. One is KVL, which is the Kirchhoff's voltage law, and another one is the KCL, which is the Kirchhoff's current law. So already discussed the KVL one. If you haven't checked the video, you can watch my previous video. You will get it in my video list. And now today we will be discussing about KCL. So first, what is KCL? First we will understand what is KCL. KCL stands for Kirchhoff's current law. The last one was the voltage law and this is the current law. First we will understand two things first. What is a node? Okay. So in a circuit, suppose we have a circuit over here. We have a circuit. It has three branches. You can see. Suppose this is this only. Complete the circuit. Okay. So the nodes are where two points meet. Okay. Wherever two or more branches meet to each other, it can be termed as node. Okay. So I can assume this is a branch of voltage potential, this is a branch, and this is a branch of resistance. These two meet at some point. We can say this point, or commonly we can say this point. Okay. So this is a node. Here three branches meet. Both three of them are of resistance. Three branches. So this is a node. Here again one battery branch and one resistance branch meet. So this is also a node. Okay, this all are called node. And another node is here also you can see three branches meet at a point. So it will be also termed as a node. Okay. So we have four nodes in this diagram, and moreover, what we can more say that, suppose can we say this is a node? The two things are meeting? No, we can't say, because the potential is same across this full line, because there is no resistance, nothing. It's just wire, and here we are assuming that the wire has no resistance, then this in a lump model, this is a lump model. Okay. So this node is same as this node, but when I go from this node to that node, there is a voltage drop. There must be a voltage drop across this resistance. That's why this is not same as this node. So I have to term is node 1, node 2, node 3. Same here, because if I go like this, there is a potential difference, and here is also a potential difference. In this particular point to this particular point, this node to this node, there is a potential difference. So this is a different node, and from this and this node also there is a potential difference. So this is also a different node. So I am turning as this node 4. But this and this is not node 5 and node 6. These all are node 4, because there is no potential change. If I suppose I put the marker here, I am going like that. I have no elements. This is the same thing, but I have changing and I have another node, because it is also a junction of two or more branches. So what is node? Junction of two or more branches. This is a node. Okay. And what is nodal potential? What is nodal potential? It is the voltage at the particular node. So nodal potential is if I say the voltage at this point is V1, it will be same across this area, This is the nodal voltage. If I say the voltage at this point, mark my words, at this point is V2, then it will be the nodal voltage at node 2. Supposedly V3 and V4. So this was important in order to learn KCL. So we discussed about what is a node and what is a nodal potential. Now we will go to the theory part of the KCL. So let's learn first easily, then we will have the mathematical equation of the KCL. So KCL states that summation of current entering a node and entering a node is equal to summation of current entering a node is equal to summation of current exiting the same node. For example, I have a node I have 4 branches, 2 ampere coming over here, 3 ampere coming over here, 4 ampere coming over here. Okay, and current is leaving through this branch from the node. It have to be 9 ampere, because let it be I1, let it be I2, this is be I3 and this is be I4. What I said, summation of current entering a node, this is a node, which currents are entering into the node, see the direction of the current, this is entering into the node. So sorry for that. So this is 2 amperes plus this is also entering into the node, 4 amperes, and this is also entering into the node, that is 3 amperes, have to be equal to 9 ampere because it is exiting the node. Okay, if I don't know this, I would have x, then equal to x, which is equal to 9 ampere. Okay, so in short, current entering into the node must be equal to current exiting the node. Or there is a mathematical way to write this equation, but first let's have an example. I said that all currents are entering into the node. None of the current is leaving the node. I1, I2, I3. Then how you will write the KCL equation? Suppose current exiting the node is 0, correct? And current entering into the node is I1 plus I2 plus I3. I know this is practically not possible because every current will be not entering into the node. Some of the current, at least in one branch, the current will be exiting the node. But even if I assume wrong direction of current, I can just simply write the equation 0 is equal to I1 plus I2 plus I3. So I need not to worry what sign or what direction of the current I am assuming while solving the problems. So that will be not a problem, because what will happen? Minus I1 equal to I2 plus I3. So that means I can theoretically say that whatever I assume the direction of that, it must be opposite, or vice versa. I can write that. Okay, so I need not to worry about any sign convention. I can choose my own direction of current and solve the questions. Just what I have to do, summation of current entering a node is equal to summation of current exiting a node. That's what I have to do. If it's 0, I have to put it 0. Just I have assumed one direction of current wrong. That will be clarified when the symbol, when the sign convention will be negative. That's the only thing. Okay. So now let's write mathematically this thing. Summation of I from all branches, summation of current in all branches across a node is equal to 0. This is KCL. What I said, summation of current across all branches around a node is equal to 0. If I assume all the current direction to be same, either entering or exiting. Okay. So if I assume, suppose n number of branches are there. If I assume all to be leaving or all to be entering a node, the summation of all these currents will be equal to, summation of all the currents will be equal to, suppose n branches, these are the branches, okay, these are the branches will be equal to 0. What we just learned. So enough of a theory, we will see a question and understand why we have to use KCL instead of KVL sometimes. Let's make a mistake also. Let's make a deliberate mistake. I have a equation, I have a circuit. This is a current source. This symbol consists of current source of 4 ampere. Okay, 40 ampere. Okay, this is 50. This is 20 amperes. So I have already learned KVL. I will some of you will say, let's apply KVL. Okay. Let's suppose I1. Let's suppose. What's the I here? It's already stating that I is this, okay? I assume that I2 like this, okay? And already the current source is maintaining a current of 4 ampere in this direction. So the loop current I2, if I assume it is this direction, it had to be -4. It had to be -4 ampere. If I assume like this, if I assume like I2 like this, it's already stating that the current source is maintaining a current of -4. This is I2 na, this is I2 na. I assume this to be I2 na. I can also assume like this also. Suppose I assume like this. Let this be I2. So I2 is 4 ampere. I2 will be then plus 4 ampere. If I assume the direction to be this, the I2 is 4 ampere. So when I will apply KVL in loop 2, let's start from this point and come again to this point and write all the voltage drop, which will be equal to 0. I come from here and going like this. I can't see a voltage drop. I can't see any voltage drop across this current. But when there is a current maintained at a fixed amperes, then there must be some potential drop. But then if not there, then how is 4 ampere current flowing? We have to understand. So there is a hidden voltage source with some load resistance so that the current is flowing, correct? So the voltage source, the voltage drop across this is unknown because this is a current source. I know only current. So I can't write the KVL loop equation is this loop. In this loop, I can't write the KVL loop equation because I don't know the potential drop. So in where there is a current source, we will use Kirchhoff's current law, and most of the times, though there are some considerations also, we will check that later. So that's why when there is a current source, we know there is a potential difference across this current source. That's why the current is flowing and current is maintained at 4 ampere, the loop current of 2, but at the loop 2, but since we don't know the voltage drop, we will have to use KCL. Okay, so that's why whenever there is a current source, we will use KCL. That's the thing. So let's write. What are the nodes? This is the node 1. So the first thing we will do is write down all the nodal potentials. Let's suppose this voltage be V1. Okay, the nodal voltage of this point will be V1. This full will be V1, and this up to this will be V1. Now, if there is a potential voltage source of 20 volt, that means the potential difference across these two nodes. Okay, this is also a node, right? This is also a node. This full is a node, and this also a node. Will be maintained at 20 volts. The potential difference across these two will be maintained at 20 volts. So I can assume anything. 22, 2. I can assume this is B. If this is 22, 22 and this is 2. So the potential difference is coming to be 20. I can assume this to be 40, 20. Then also 40 minus 20, it will be 20 volts only. But for simplification and calculation purposes, what we use is, this is 20 volts, we will have potential 0 over here, and we will assume this to be 20, plus 20, and this is 0. So the potential drop across this point is 20 volts only. So we can easily tell that the potential, the nodal potential at this point, okay, is equal to 20 volts, okay. So the potential at this node is 20 volts, at this node is V1, at this node it's also V1 because there is no resistance and no potential drop across that, and this is also 0. So how many equations you can form? See, there is a junction of 3 branches, I can form an equation from there. Let's assume currents are flowing. Here the direction is also mentioned, the current is coming towards this node, okay, I2, already given as 4 ampere, is coming towards this node, okay. Let's just assume 2 other currents. A total current of I1 is flowing through this branch and I3 is flowing through this branch, okay. Randomly just take any direction. You want to take like that direction, you want to take like incoming current, outgoing current, it's your choice. The sign convention will handle it automatically, okay. So even you can assume the current to be this, but the value of I2 will be minus 4, that's it, because the current source is maintaining a 4 ampere current in this direction, but you are assuming that direction. So you will just have to reverse the polarity. But for making it simple, already given the current direction, I will assume to be like this. So it will be 4 amperes. So applying KCL, okay. I1, these are the currents which are leaving the node, and this is entering the node. So summation of entering the node is equal to exiting the node. I1 plus I3 equal to I2 equal to 4 amperes. Equation, I framed the equation, okay. So how can I write I1? I1 is this. So how to write current? We all know that voltage equal to IR. So current will be equal to voltage by resistance. So simple. So what is the voltage drop across this if I am assuming the current is flowing from this direction to this direction, current always always flow from higher potential to lower potential. So I have to, if I have assumed this direction to be current, assume that I also have to assume that V1 is greater than 0. Okay, I have to assume that. So V1 minus 0, this is a potential drop across this resistance upon the resistance is equal to current V by R plus what is I3? What is I3? V1 minus V2. I have assumed this direction, so V1 minus V2. V2 is 20 volt. The potential at this point already known. So V1 minus 20. V1 minus 20 upon the resistance is 50 ohms. Okay, upon the resistance is 50 ohms is equal to 4 amp. Correct? Okay, so now let's simplify this. V1 by 4 plus V1 minus 20 by 50 equal to 4. So I just find this nodal potential. Okay, so what will be the, let's do a so implies that 90 V1 minus 80 equal to 800. 90 V1 equal to 8. 80 V1 equal to 8. 80 by 90. So I got the V1. So how to know what will be I1? I1 will be V1 by 40. So I1 equal to V1 by 40, which will be equal to 880 by 90 upon 40. Simple. Okay. So it will be equal to 880 upon 40 into 90. Sorry for that, the camera got disturbed for a second. So we were finding V1, I1. So I1 was V1 by 40 and V1 was 880 by 90. So I1 will be V1 by 40. So V1 by 40, which will be equal to around 2.44 amperes. Okay, 2.44 amperes. And now how to find I3? Okay, I3 will be easily found out by this equations. I1 plus I3 equal to I2, which is equal to 4. So I1 plus I3, I said, will be equal to 4. And I already know the I1 is 2.44. Let's suppose plus I3 equal to 4. So I3 will be equal to 4 minus 2.44, which will be equal to 1.36. Okay, 1.56. Sorry. Okay, so I3 will be equal to 1.56 amperes. Okay, so this will be equal to I3, and we already found out I1. Okay, so therefore we can now easily say anything. What is the potential across this resistance? It will be 50 into I3. Sorry, 50 into I3. What will the potential across this resistance? It will be I1 into 40. Okay, so we can solve each and every question which is framing well. So that's why we have to use sometimes KCL. It can be also used for multiple loops, questions with a current source. But the more the loops will be, there will be, this is the more the loops will be there with current source, there will be more equations and more you have to find out. Okay, so KCL is also required whenever there is a current source present in a circuit, because we don't know the potential drop across this, hence we have to use the summation of currents entering into a node is equal to exiting a node. Sometimes we have to use. So this was KCL. So what now next I am going to do is take a lot of problems, difficult problems from starting easy problems to difficult problems to help you with our semesters, and also I think 11, 12 also these things are there, so it will be if someone is watching in this who are not in engineering but also in suppose 11, 12, they will be also beneficial from the same, and also the engineering first year students will also beneficial from them. After completing the current circuits, I will also do many videos on control systems and etc. and etc. Electrical machines. So keep watching my videos and do subscribe my YouTube channel. Hope this will help you. Thanks.